This
Reason why it
conference
is
will now
overheating,
be recorded.
there must have been some garbage data which has been put into the port D register, which is why your LED must have been behaving that way. So if you want to turn it off, you can use the second DIP that has to be against port D. So if the second DIP, if you put it towards LED 1, then in that case, your port D LED will not be glowing. So if you want, you can do that. If you don't want port D to be seen. Okay, fine. So yesterday we wrote this program, and this particular program was to toggle all 8 LEDs which are connected to port B. And even after this, we saw few other things also, like few other patterns as well we saw. So we tried turning on 4 LEDs alternatively. Then we tried turning on one after the other, LEDs alternatively. Then we also did a classwork of turning on the LED from top to bottom. I see that some of you are trying to do the turning off of LED from the top to bottom. So I would suggest you, if you people have not done it yet, or if you are still trying it out, I would suggest you to avoid right shift, because in case of right shift, there is signed right shift, unsigned right shift, which you may get confused depending on the data type. So ignore, always try avoiding right shift if possible, and try doing the turning off of the LED. And I hope you are able to do that, because after turning it off, again you have to turn it on from the top. So how you are going to perform it, you have to take a call. So after you have turned off all 8 LEDs, again one after the other it has to be turned on, and again one after the other it has to be turned off. And Ajinkya, I said you, like yesterday we spoke about it, you are asking for delay with respect to the milliseconds with the help of built-in function instead of for loop. So please have patience, I'll show it after certain topics are covered. Okay, so as of now, please ignore using it. All right, so let us continue. I was telling there is one small topic with respect to the LEDs itself. Now tell me, what was the reason for us to take this for loop? What was the reason for us to take this particular for loop? It was to add certain delay. Okay, so we had to add some delay here in order to see the output visually on the board. So we added a delay to kill some of the time of the compiler. Now the problem with this is, what this statement does is, it is actually blocking the particular controller for certain amount of time. So this is actually blocking the controller for certain amount of time. So we call this for loop as a blocking delay. Okay. So the name given to a delay which has been introduced using the for loop is nothing but blocking delay. Now let me make you understand why do we actually call it as a blocking delay. Now assume after the for loop's execution, I have to read a switch from the user. So you don't know how to read a switch from the user yet, but I want to read a switch from the user. Okay, so I'm writing it as a statement. Now assume you are keeping the switch pressed for around 10 milliseconds. Okay, so you are keeping the switch pressed for around 10 milliseconds. And this for loop, assume it is taking 1 second to completely execute the for loop. So just an assumption. So it is taking 1 second to completely execute the for loop. And guys, please trust me, when it comes to the embedded system, milliseconds also is a large time. Okay, you cannot even ignore milliseconds. Milliseconds is also a large time. Now what happens in this case is, assume this is the program you have executed on your microcontroller, and microcontroller starts executing the code. Okay. So first what it does, it is going to execute port B is equal to complement of port B. So that output you will see it on the board. Okay. Similarly, after that, your control will start executing the for loop, which is approximately taking 1 second. Okay. Assume when your software is busy executing this for loop, in the hardware, assume you press the switch. Okay. So your software is busy executing the for loop. It can come out of the for loop only after 1 second. Meanwhile, in the hardware, you are pressing the switch for approximately 10 milliseconds. Now, what happens with this for loop is, when I have pressed the switch in my hardware, do you think your software will be able to identify the switch press immediately? Do you think your software will be able to identify the switch press? No. So that is not possible. It is not just may, I would say definitely not possible, because your for loop is taking 1 second for its execution. Your controller is busy executing the for loop. Meanwhile, in the hardware, you press the switch. Now, by the time you come here and see if I have pressed the switch, I have lost that event. So at that time, after 1 second, if I come and check, obviously the switch will not be checked. So I will decide that the switch is not pressed. So what this for loop always does is, it is always going to block the controller by making it busy. Okay. So it is always blocking this particular microcontroller. So that is why such kind of a delay which is introduced with the help of loops, we call it as blocking delay. And it is always not suggested to have a blocking delay return. So you always have to try writing a non-blocking delay, so that the delay whatever you have written is not affecting any other operations in your program. So you always have to write a non-blocking delay. Now, how to write a non-blocking delay is the question. Observe this and tell me, after how many iterations this statement is getting executed every time? After how many iterations this statement is getting executed every time? After 50,000 iterations, this statement is getting executed every time. So I can do the same with the help of an if block itself. So anyways, I'm inside while of 1. So no issues with while of 1. It is leading to an infinite loop. So I have to make sure this statement, whatever I have written. So for this only I added the delay. Whichever I wanted the delay, understand that this statement is getting executed after 50,000 iterations only. After every 50,000 iterations, I am getting the statement executed. I can do the same with the help of an if block also. So first, I'll take an unsigned long integer variable called let's say weight. Okay, and I am going to assign it with 50,000. Okay, so unsigned long integer. Am I not audible? Guys, if you are not sitting on a stable internet, please check with your internet once. Okay, so yes, unsigned long integer weight is equal to 50,000. So what I will do is, I will write an if block here. Okay, so if weight minus minus, you either can take pre-decrement or post-decrement. So if minus minus weight is equal to 0, I am going to make weight back to 50,000 and I am going to perform this operation. Okay, something like this. Don't you think even now this operation will happen for every 50,000 times only? Yes, can you observe? See, first while of 1, you are inside a while loop. So minus minus weight, so it is 50,000 initially. So this is going to be 49,999. Okay. So equal to 0 is condition false, you don't operate. Again you come back here, you take 49,998. So that is also not equal to 0, so you don't perform the operation. When weight turns out to be 0, 0 equal to 0 will be true. You will assign weight back to 50,000 and you perform the operation. Again you come back after 50,000 iterations only, this statement is getting executed. And this we call it as non-blocking delay because my control is not getting stuck anywhere. If you properly observe here, my control is not getting stuck anywhere in this. So every statement, whatever you have written, hardly takes 1 or 2 microseconds or milliseconds to get executed. So I'm not having any statement return which is getting my control stuck for a certain duration. And I'm also making sure that this statement is getting executed for every 50,000 times only. So that is nothing but non-blocking delay. See, our focus is to execute port B is equal to complement of port B for every 50,000 iterations. So here also, after every 50,000 iterations only, so I'm going to do port B is equal to complement of port B. So this is non-blocking delay and it is also letting the operation perform for every 50,000 times. Is that clear? So this is non-blocking delay. So in all of your programs, writing non-blocking delay at once is not easy. So first you can write a blocking delay and then you can convert it to a non-blocking delay. Then any major difference in time when compared with the for loop? Actually, no. Not much of a difference between the for loop and the while loop. I mean, for loop and the if block. So both of them comparatively will give the same amount of time. Okay. And guys, if you are not stable with the internet, please make sure you're sitting with the stable internet. Now each one of you, if you ask me to repeat the same topic just because of the issue with the internet, then it will be difficult for me to go ahead. Okay. Didn't understand how for loop delay is blocking delay. So as I said, this for loop, your control, when it enters to execute this for loop, okay, it will be able to come out of this for loop only after you complete executing the for loop. So until the loop is not completely executed, you will not be able to come out of the loop. So your control is being blocked in this for loop itself. So your control is being blocked in the complete for loop itself. So that is blocking delay. So it is blocking the control. Okay. And if you go with the non-blocking statement, non-blocking delay or non-blocking statement is a replacement to the blocking statement. And if you observe here, I have replaced it with the if block. So if minus minus weight is equal to 0, I'm only making sure this statement is executed after 50,000 iterations. So that was happening here also. After 50,000 iterations only, this statement was getting executed again and again. So I am also making sure to execute this statement only after 50,000 iterations. So if minus minus weight is equal to 0, this condition will be true only after 50,000 iterations. So once the condition is true, you will make weight back to 50,000 and execute the statement. Here, if we write any statement after if block, it won't wait for no. See what is happening, how is the control going? First, it will come here. Okay, if condition is false, so it will come here and check if the switch is pressed. It hardly takes, approximately assume 1 millisecond for its execution. So this will also take 1 milliseconds for its execution. So it doesn't matter. See, you have pressed the switch for 10 milliseconds. So if you were at this point of time, so you check the condition is false, you come here, you will be able to read the switch immediately. Even if the condition is true, you will enter into the if block, you execute two statements which approximately takes 2 milliseconds for its execution, and when you come here, you will still be able to read the switch. So that is non-blocking delay. Okay, and in if else isn't control, how do you think the control is getting blocked? Blocked means it should consume more time executing the statement. Okay, so think, and like you literally think, if it is a for loop, observe the whole for loop should get executed, and only then you will be able to come out of the for loop. So that is blocking. And if block is never blocking. So if block will always make sure the statements are executed one after the other on time. What if switch is pressed when the if block is running? So as I said, when the if block is running, so if block hardly takes around let's say 3 milliseconds for its complete execution. Okay, so only three statements have to get executed: condition check, way should be assigned, and port B is equal to complement of port B, approximately 3 milliseconds. I have kept the switch pressed for 10 milliseconds. So when I come here, I will still have the switch pressed, and I will still be able to read the switch press being done. And yes, because I have returned inside while of 1, it is possible. If I would have not returned it inside while of 1, then this kind of operation wouldn't be possible. So only because I'm inside while of 1, this kind of operation is happening. And we call it as a non-blocking statement. Understood now? Okay, so that was about the blocking and the non-blocking statements. So always you have to avoid using the blocking delays. So for loops, we always suggest not to use the for loops. Okay, so for loops are always either it is a for loop or a while loop. Having while of one return is necessary. Apart from while of one, you should never be using any of the blocking statements like a for loop or a while loop. Apart from this loop, there should not be any other loop running in your program, because that is going to block your control until you come out of the loop. So whatever program we wrote yesterday, so I am going to change that also. So whatever we wrote for the blocking delay, I have to change it for the non-blocking delay as well. Now observe how we are going to make the change. Give me a second. The MP Lab XID is still loading. So it takes few seconds to get loaded. It is like literally taking too much of time. Okay, so you can observe here. So let me open. So I'm already in main.c file. Okay. Um, okay. So you can observe here. This is the first blocking statement. Okay. So it is taking for 1,50,000 iterations. So whatever it is for I is 1,50,000 iterations. So my reason for having this delay return was to make sure this LED array, whatever I have written, should get executed after every 1,50,000 iterations. So first I will change this blocking delay into a non-blocking delay, for which I need an unsigned long integer variable called I, return with the value 1,50,000. Okay. So this I'm going to remove, and I should write a non-blocking statement. So if, okay, so I have to do minus I is equal to 0, then I have to do this operation. And one more thing, I have to write I back with 1,50,000. So I is equal to 1,50,000. Are you able to follow this? So whatever for loop I initially had, I'm trying to convert it into non-blocking delay. So if minus I is equal to 0, I is equal to 1,50,000, and I'm making LED is equal to LED left shifted for ones or with one time. So this is first replacement of a blocking delay. But this for loop which I have written is again a blocking statement. Okay. The for loop I have written is again a blocking statement. So what I have to do is, all of the statements I have written should get executed for how many times? All of these statements I have written should get executed for 8 times. Correct. So I again have to replace this in such a way that this is getting executed for 8 times only. Okay, so I have to make sure this is getting executed for 8 times only. Now I take a character variable called I. Okay, it is J, return with the value 0. So instead of this for loop, I will write if, okay, so if J is lesser than 8, I have to perform the operation. So this has to happen. Can you tell me where will I increment the value of J? Where will I increment the value of J? I have to make sure this if block is getting executed for after if line number 34. So that means, do you want J plus plus to be written here? Okay. Now see what happens in fact. So I have taken J with the value 0 initially. So you are already inside while of 1. J lesser than 8 is condition true. Okay, 0 lesser than 8 is condition true. So you enter into the if block. Now minus I is equal to 0 is condition false. So you don't enter into the if block. So you are doing J plus plus. It will be updated to 1. Again you come back here. 1 lesser than 8 is condition true. Then you enter into the if block. This condition will still be false. You will not end up taking the action. See, by the time you execute this, you don't even get a chance to execute this actually. So even before you get a chance to execute this, J will be updated to 8 by then. So I have to update J++ only after I take the action for once, right? Only after I take the action for once, I have to update J++. So this is the right place to do J++. Okay. After I toggle one LED, I want the next LED to be taken. So I will do J++. So this is replacing blocking statements with non-blocking statements. Now the behavior will be almost the same. So a small delay will be increased. If I took for loop with a delay of 1,50,000, it was approximately giving me around 2 seconds. This time it might give me 3 or 4 seconds because I have more number of instructions written. Okay, so there will be slight difference in the time, but the operation is going to remain the same. Now I'm just waiting till the loading gets completed. Okay, so build is successful and loading is completed. We are taking character J as it takes less bits. Can we also take int J? Yes, you can, but it is just a waste of memory in that case. So load hex, I'm going with the same down desktop MC class 23000811 LEDX distribute default production the hex file, and I hope it is okay. It is port D. Okay, so observe, I'll do the reload last. So observe the output. LEDs are getting turned on one after the other itself. But this time, instead of blocking statement, I have written as a non-blocking statement. So you always have to avoid writing for loop or while loop in your application code. So that is going to block the statements. Understood this? Everybody, is this clear? Okay. So this completes the first peripheral of your module, which is nothing but the LED. So I'll go with digital keypad, the next peripheral. But before that, if you want, you can note this down. Hmm. I am trying to create an individual SRC file for LED blinking, toggle, and train pattern in the same LED project under source file folder, but getting error while generating. Okay, so Babu, please understand you cannot have multiple source files return because the problem is while compiling, all of those source files will be compiled under a same project. So if you want separate source file, you have to choose to go with separate project itself. In the same project, you cannot have different source files written with multiple logic. So while compiling, all of them will get compiled together. If you can post message to everyone, it will be better for our understanding also. Uh, should I post message to everyone, Chaitanya? If you're asking the other person to do it, okay, okay, fine. And yes, that is right. To make sure each of you are hearing to it, I generally read out the questions aloud. Okay, so let us proceed. If switch is pressed for 1 millisecond, we will still not be able to read the data, right, using the if also. So that is like really a very exceptional case. So in that case, you will not be able to identify the switch press in any scenario. So if you are pressing it for only 1 millisecond, okay, or 1 microsecond if you take, so in that case you will still not be able to like read in any kind of a situation you write. So your program should only have a statement to read the switch being pressed. Apart from that, anything else being involved, you will not be able to anyways read it. So that is like a very rare scenario of in that case you have to use the concept of interrupts and all. But just for the justification of my statement, I had to take this particular example. So don't take things in a very sensitive manner. Okay? Okay, fine. Okay, and yes, all of you, please try texting or saying anything in the chat box which is visible to everyone rather than doing it to the organizer or presenter only. So please make sure you're using the chat box to everyone. Okay, fine. So let us continue with the next peripheral. So this completes the first peripheral, which is nothing but LED. Now starting with the next peripheral, we have got a digital keypad. So digital keypad means it is just a combination of switches, or I can say the group of switches, we together call it as a digital keypad. So we are going to start with that particular peripheral in today's class. So first I have some theoretical topics to be discussing about the digital keypad. It's not the matrix keypad. So we are talking about as a digital keypad. So in this particular uh, topic, which is nothing but the digital keypad, we have to first start with the introduction to the digital keypad, then different interfacing of the digital keypad, then input detection. So how are you going to detect the input in the digital keypad? Then we are going to see the bouncing effect. So like how the bouncing effect is uh, playing an important role in the digital keypad, something which is really necessary to be taken care of. And the last, how the circuit is available on our board, how digital keypad is available as a circuit on our board. So we are going to start with the digital keypad in today's class. Now to start with the very first, we go with the introduction of the digital keypad. Now, this is the very simple and the cheapest interface when it comes to the digital keypad. So, this is offering you a simple interface. So, it is the one which helps you in the human machine interface. So, whenever you, being the human, want to give any input to the machine, you have to make use of any human machine interfacing. And the switch, in fact, is like the very simplest kind of an interface you can create. And these switches comes in different shapes and different sizes also. The switches can be of different shapes, the switches can be of different sizes as well. And we prefer to go with digital keypad only if we have got less number of user inputs. Okay, so this topic I'll actually revisit when we go with the matrix keypad. So if the user inputs are less, we prefer choosing a digital keypad. If the user inputs are more, we prefer choosing a matrix keypad. So preferably, whenever we have less number of inputs to be taken from the user, we will go with the simple digital keypad. And the configuration is mostly based on tactile switches. So all the keys of a digital keypad is being made up of a tactile switch. So we have to understand tactile switches operation in general. Then if you look at the applications of these tactile switches, it has been used in, as I said, human machine interfacing. Then it can be used in your mobile phones, your power button, your volume up button, volume down button. So that is also made up of a tactile key, and your computer mouse. So that is also made up of a tactile key. So these are the applications where tactile keys are commonly used. So we are going to start with the very first type, the very first important human machine interface, which is nothing but a digital keypad. So LED is a feedback device. Okay. So LED is always a feedback device, and the digital keypad is nothing but human machine interfacing peripheral. Now, whenever you have to take a switch, okay, so as I have already told you, if you have to represent a switch, you will take two notches. Okay, so something, okay. So you will take two notches like this, and you will have a horizontal line and a vertical line. So if the switch is not making the contact between the two notches, then the switch is said to be open, or the switch is not pressed. Okay, so we very commonly refer it as open. And similarly, if the connection is being made between the two notches like this, then we call the switch as closed. Okay, so I can commonly refer it as pressed, and technically I can say the switch is being closed. Okay, so technically if the switch is not pressed, we call the switch as open. If the switch is pressed, we call the switch as closed. Okay, now basically we will start understanding the working of a digital keypad. In fact, digital keypad is a combination of switches or tactile keys. So first we will understand how will these tactile switch work, and then we will combine them together to form a digital keypad. Okay. So initially to start with, so let me take you to this slide. So this is the first way of getting a switch connected. Okay. So first way of getting a switch connected. Assume there is a microcontroller here. Okay. So this is an RB0 pin of your microcontroller. Okay. So this is RB0 pin of your microcontroller. Now tell me, what are you going to read at this pin of the microcontroller whenever the switch will be pressed like this? So if the switch is pressed or the switch is closed, what are you going to read at the pin of the microcontroller? So it's a 0. Okay, because current from the microcontroller will be flowing to the ground like this. So at this pin of the microcontroller, you will be identifying a ground. So remember, ground is always represented digitally as 0. Okay, so digitally ground is represented as 0. So if you are going to get the switch pressed, current from the microcontroller is flowing to the ground, and you will be able to read a 0 at the pin of the microcontroller. A ground is identified, so you will be able to see a 0 at the pin of the microcontroller. Now what if the switch has been open? What happens if the switch has been open? What are you going to read at the pin of the microcontroller if the switch is open? So something like this. The switch is open. So I have not made the complete circuit connection. So what are you going to read at the pin of the microcontroller here? Is it a valid one? Okay, yes. So the line, you call it as a floating line because the circuit is not complete. Okay, you call the line as a floating line as the circuit is not complete. So this point, if you see with respect to the connection, It has not been connected to anywhere. So it's an open circuit, and the line is called as the floating line. Now, due to this floating line, there are chances where the noise around the line can get attracted, and it might lead to give me a 1 here. Okay, so there are chances that the noise around the line will get attracted, and I might end up getting a 1 here at the pin of the microcontroller. But do you think it is a valid one? Is it a valid one if I get a 1 here? Obviously no. So 1 what I got was because of the noise, not because of some valid input I have provided. So that is always a problem. Whenever I'm not keeping the switch pressed, I might end up getting a 1 seen which is not valid. I might end up getting a 1, I might end up getting a 0 also. So if no noise attracted, I might see a 0. If noise is attracted, I might see a 1. It can be anything. So in order to avoid this situation, whenever I don't press any switch, I am going to add a VDD connection. Okay, so I'm going to provide the voltage on the other side. Now see what happens. Whenever the switch is not pressed, what will I get here at the pin of the microcontroller? I will be getting a 1 because the current from VDD will be flowing into the microcontroller. Okay, so current from VDD will be flowing into the microcontroller. So I will end up getting a 1 whenever the switch has been open. What if the switch is closed? What if the switch is closed? Do I get a ground scene? If the switch is closed, do I get a ground scene? Okay, so if you see the switch pressed, don't you think the entire current from the VDD flows to the ground like this? So will it not go completely to the ground? And what do we call such situation as? The complete current from the VDD is flowing to the ground. You call it as short circuit. And short circuit is more dangerous than that of a floating line. So it is okay to keep the line floating, but having a short circuit is more dangerous than that of a floating line. So what I have to do is, I cannot let the complete current from the VDD flow to the ground like this. In between, I have to add a passive device which consumes some power. It acts as a load, so it's a passive device. It consumes some power, and it is basically acting as a load, feeling that the current is not completely flowing to the ground. So what I can do is, I am going to add a resistor along. So if you can see here, I'm adding a resistor along. So now what happens? Whenever the switch is open, okay, so whenever the switch is open, current from the VDD is flowing to the microcontroller. So you will be reading a 1 at the pin of the microcontroller. And whenever the switch is closed, current from the VDD flows to the ground via the resistor R1 and switch 1. Okay, so current from the VDD flows to the ground via the resistor R1 and the switch 1. So you will be able to identify a ground here. So whenever switch is pressed, you will be able to read a 0 at the pin of the microcontroller. Are you understanding this? Okay. So I will preferably have it written as a document. Give me a second. Hmm. Okay. Hmm. So this I'll erase because you know what is open and closed by now. Okay. So I'm going to add here, insert. Okay. So this is the circuit. So I'm going to have a controller connected here. Okay, so this is the microcontroller, and this one is the RB0 pin of your microcontroller. Okay, it's the RB0 pin of your microcontroller. So I'll mark the difference. So whenever the switch is been, I'll see the state. So switch state, okay, then value at RB0 or value at microcontroller pin. Okay. So first I have two states of switches. One is the on state. I'm going to have it return in this, or I would say switch is being uh, open. Okay. So whenever the switch is open, what am I going to read at the pin of the microcontroller? So it should be a 1 because the current from the VDD is flown to the microcontroller. So I'll draw it here. So current from the VDD is flown to the microcontroller. So you should be able to read a 1 at the pin of the microcontroller. Then second state is switch being off. Switch being closed. Okay, so I'll write it in another color. So closed. So what am I going to see? It's a 0. Okay, it's not a short circuit. I have added a resistor now. So it should not be leading to any short circuit. So current from the VDD flows to the ground via the resistor R1 and switch 1. So you should be able to read a 0 at the pin of the microcontroller. Are you able to understand this? Okay. And this is why short circuit is dangerous. So generally, if you go with short circuit, obviously it is going to damage all the devices which are connected in that network. Okay. So floating line will not harm any devices as such. It might attract noise, but it is not going to harm any devices. But due to the short circuit, there are chances where all of these devices might get damaged. Okay. So a short circuit is always more dangerous than that of uh, a floating line. Okay. Yes. So this is the first circuit, and we have got a name to be provided to the circuit. So the name for the circuit is provided according to the register I'm using, the R1 register. And this kind of a circuit is called as a pull-up circuit. Okay, so this is called as a pull-up circuit. Now, why do we call it as a pull-up circuit is, if you take the task of this resistor R1, okay, if you take the task of the resistor R1, it is performing two tasks. First one is, whenever the current from the VDD is flowing to the microcontroller, okay, in the first case, if the switch is open, current from the VDD is flowing to the microcontroller. So you are not letting the complete current from the VDD also flow to the microcontroller, because there are chances that it might also damage the pin of the microcontroller. So this R1 is acting as a load in the first case also. When the switch is open, So R1 is also acting as a load. It is not letting the complete current from the VDD flow into the microcontroller. In the second scenario also, that is when the switch has been closed, R1 is still acting as a load so that the current from the VDD is not flowing to the ground directly and causing a short circuit. So R1 here is acting as a load in both the scenarios. So that is the first work of resistor R1. And the second work of resistor R1 is, so we give the name as pull up because you always consider the state of the switch as open. Okay, to give the name for the circuit, we generally take the state of the switch as open. So whenever the switch has been opened, the line is being pulled up. Okay. So whenever the switch has been opened, the line is not pulled down. The line is pulled up by this VDD via the resistor R1. Pull up in the sense, even if the switch is open, you are seeing a 1 at the pin of the microcontroller. So the line has been pulled up even if you have kept the switch as open. So that is why we have got the name given to the circuit as a pull up circuit. So this is one way of getting the switch connected to the microcontroller. One end of the switch is connected to the microcontroller, another end of the switch is being connected to the ground. So if the switch is being closed, you will read a 0, but if the switch has been open, it was always leading to a floating line. So to avoid the floating line, you pulled the line up adding a VDD, but that led to a short circuit later. So you added a resistor called R1. So this R1 pulled the line up and you are able to read a 1 whenever the switch is open and read a 0 whenever a switch is closed. So the first way of switch getting connected to the microcontroller is like a pull up circuit. Understood this? Everybody, is this clear? Okay. So there is another way of switch being connected to the microcontroller, that is like a pull down circuit. So observe the second way of switch being connected to the microcontroller. So it's something like this. Okay. So this is the second way of getting the switch connected to the microcontroller. So I have a switch like this. I mean a microcontroller like this. So one end of the switch is connected to VDD. Another end of the switch is connected to the microcontroller and also to the ground via the resistor R1. So what happens if you press the switch? What happens if you are going to press the switch? What are you going to read at the pin of the microcontroller? If you press the switch, will you see a 1? Current from the VDD is flowing to the ground. So there will be a ground identified at this pin. Okay. So there will always be a ground identified at this pin. So what are you going to read here if the switch is closed? So you are, one second. Oh yes. So whenever the switch is closed, what is happening? So current from the VDD, yes, I'm sorry, yes. So whenever it is correct, yes, I'm sorry, one second. Okay, yes, please wait. So I am taking a microcontroller here. So I'm asking, okay, it's in the reverse state. So if I am not pressing the switch is open, what are you going to read at the pin of the microcontroller? So if the switch has been open, current from the microcontroller is flowing to the ground. So I should be able to read a 0 at the pin of the microcontroller, correct? So whenever I press the switch, current always takes its easiest path to reach the ground. Okay. So whenever I'm going to press the switch, current always takes its easiest path to reach the ground. Now, because current takes its easiest path to reach the ground, it is going to enter the microcontroller rather than flowing via the resistor R1. Okay. So rather than flowing the current to the ground via the resistor R1, it is going to enter the microcontroller. So I am going to read a 1 at the pin of the microcontroller, correct? But okay, I'm repeating again. So if the switch has been opened, okay, so first state I took was if the switch has been open. So when the switch has been open, so current from the microcontroller is flowing to the ground and you will be able to read a 0. If the switch has been closed, current should find its easiest path to reach the ground. So current can either enter the microcontroller or it can reach the ground via the resistor R1. But because it has to choose the easiest path, it chooses a path which doesn't involve any load. So current from the VDD will flow directly to the microcontroller and I am going to read a 1 at the pin of the microcontroller. Now look at this and tell me, is there any problem in the circuit? Is there any problem in the circuit? Any potential issue in the circuit? No potential issues? Okay, think when I have kept the switch pressed. Okay, so think when I have kept the switch pressed. Don't you think more than the required current is going to flow to the microcontroller? So don't you think more than the required current might get flow into the microcontroller? Yes. Now how to avoid this? It is possible. Okay. So it is possible. The complete current without any load is being given to the microcontroller's pin. So more than required current is flowing to the microcontroller. So due to this, there it can be a damage caused to the pin of the microcontroller. So how to avoid this is, I should add a load, a resistor like this in such a way that this is consuming some power before it is being put to the microcontroller. But the problem with this is, this resistor what you are going to add, you have to make sure even after you add the resistor, your current should flow to the microcontroller itself. Okay, so even after adding the resistor, your current should flow to the microcontroller itself. So there is a rule to be followed. This R2 should be 10 times lesser than that of R1. Okay, so this R2, if you take 1 ohm, then R1 has to be 10 ohms. Okay, so remember R2 should always be lesser than R1. Only then current from the VDD will flow to the microcontroller whenever you press the switch. So if you interchange the sizes of the resistor R1 or values of the resistor R1, then current from VDD will flow to the ground. Even after you press the switch, you will read a 0 itself. Okay, you will not be able to identify the switch press. So you have to add a resistor in such a way that this particular resistor is kept as low as possible compared to that of R1, at least 10 times lower than that of R1, so that current is still flowing from the VDD to the microcontroller. So you always have to remember this. There is a rule that R2 has to be lesser than that of R1, at least 10 times lesser than that of R1. Okay, and this kind of circuit is called as a pull down circuit because whenever you keep the switch open, okay, so whenever the switch has been in the open state, so remember this resistor R1 is pulling the line low. Okay, so it is pulling the line low, so it is called as a pull down circuit. So let me also note that here. Okay, I'm saving this. So this is the second way of having the switch connected to the microcontroller. So I'm taking the microcontroller here. Okay, so this one is the microcontroller. So this kind of circuit is called as a pull down circuit. Okay, this is called as a pull down circuit. And here also I'll make a table, switch state. So switch state and value at microcontroller pin. Okay. So now first to say if the switch has been open, what are you going to read at the pin of the microcontroller? Come on, please repeat again. If it is open, so you are going to read a 0, and if it is closed, what are you going to read? Yes, it is a 1. So this is closed and this will be a 1 here. Okay, and let me show this. So switch has been open, current from the microcontroller will flow to the ground and you will be reading a 0. If the switch has been closed, current from the VDD will flow to the microcontroller and you will be reading a 1. So the only problem or challenge here is R2, okay, should be, okay, I would say 10 times of R2 should still be greater than R1. Okay. Or I would say R1 has to be at least 10 times greater than that of R. I think this is lesser than. So 10 times of R2 should still be lesser than that of R1. Or I can say R2 has to be lesser than 10 times that of R1. Okay, so something like that. So if R2 is 1 ohm, okay, so if R2 is 1 ohm, R1 has to, why R2 value is less? Because current always finds its easiest path to reach the ground. Noise. Somebody's mic is on. Please check. Okay. So I was telling why R2 should be lesser than that of R1. See, if R2 is not taken lesser than R1, current always finds its easiest path to reach the ground. Okay, whichever is having the lesser load, that path will be chosen for the current to be flown. If by chance you take R1 lesser than that of R2, okay, So current will flow from VDD to the ground via switch 1 and R1. So I will be reading a 0 even after I press the switch. I will not be able to differentiate whether the switch is pressed or not in that case. So I have to make sure current from the VDD is flowing to the microcontroller whenever the switch is pressed, and that is possible only if you take R2 lesser than that of R1. Got it? Okay. So that is about the two states. Okay. I mean the two ways of having a switch connected to the microcontroller. You either can connect it as a pull-up circuit or you can connect it as a pull-down circuit. Is that clear? Okay. So note it down. I'll continue in 2 minutes. Give me 2 minutes. Okay, let us continue. Okay, Srikar Desai is asking, in pull-up circuit, switch is closed, then some amount of current is going to the microcontroller or not, which is closed. So no, it is going to go to the ground itself directly. See, after it has crossed resistor R1, see in case of pull-up circuit, crossing resistor R1 is compulsory. Whether you want to go to the microcontroller or it wants to go to the ground. Now what happens is reaching the ground is easy via switch 1 than going to the microcontroller and then reaching the ground. So if the switch is pressed, always from VDD current flows to the ground in the pull-up circuit. Okay, fine. So next one more thing, whenever you take the switches into consideration, so you are supposed to take the action. When do you think you will take the action? When the switch is pressed or when the switch is released? Always if you have to take action, well, will you take the action when the switch is pressed or switch is released? Yes. So always you will end up taking the action whenever the switch is pressed, not when it is released. So if you have to take the action upon switch being pressed, you can take the action either with respect to the edge detection or with respect to the level detection. So whenever a switch is pressed, there are chances that you will get either of the two edges identified or either of the two levels identified. So this is called as edge triggering. Okay. And the signal falling from high level to low level is called as a falling edge. Okay. And the signal rising from a low level to high level is called as a rising edge. Okay. So falling edge and the rising edge. Similarly, throughout the level, if the signal is high, it is called as high level. And throughout the switch press, if the signal is low, we call it as low level. Now, let us discuss which edge gets identified and which level gets identified whenever you are going to press the switch in each of the circuit. Okay. So instead of assuming this as RB0 pin, for time being, assume this as the pin of your CRO. Okay. So assume this is the pin of your CRO. So this time you will be observing a waveform. Okay. So you will be observing a waveform. Now think and answer. So whenever I have not pressed the switch, okay, so assume the switch is not pressed, switch is open. What are you going to see at the pin, at the CRO pin? So switch is not pressed, means switch is open. You will see a 1 which is nothing but VDD. Okay, so it's a VDD. Now the moment you press the switch, what are you going to see at the CRO? The moment you press the switch, what are you going to see? It's ground, okay, which is 0 volts. So when you press the switch, the signal will fall down from high level to low level. Do you agree? When you press the switch in this particular circuit, the signal is falling down from high level to low level. And as long as you keep the switch pressed, what will you identify? As long as you keep the switch pressed, what is read at the CRO? You keep reading a 0 itself. Okay. So you keep reading a 0 itself. And the moment you release the switch, what are you going to see at the CRO? The moment you release the switch, again a high signal. Okay. So the statement I'm going to make is, whenever a switch is pressed in case of your pull up circuit, okay, so when the switch is pressed, remember you are going to identify a falling edge, and throughout the switch being pressed, you are going to see the low level. Correct? Am I right? Okay, so please understand. So whenever I am keeping the switch open, I will be reading a 1. The moment I press the switch, the signal falls down from high level to low level. And throughout the switch pressed, I will be reading a 0 itself at the CRO. So I am going to identify a falling edge whenever a switch is pressed, and I am going to identify a low level when the switch is pressed in case of a pull-up circuit. I hope you are getting. Now coming to the pull down circuit. Okay, the next I have another kind of circuit which is the pull down circuit. So what happens in the pull down circuit? Whenever a switch is open, what are you going to read at the pin of the CRO? If the switch is open, what are you going to read? So it's a switch is open. You are going to read a 0, which is nothing but ground. The moment you press the switch, what will you read? The moment you press the switch, you are going to identify a VDD or 5 volts. So signal rises from low level to high level. And as long as I keep the switch pressed, what will I read here? As long as I have kept the switch pressed, I keep reading a 1. Okay. So I keep reading a 1 as long as I keep the switch pressed. The moment I release the switch, so I'm again ending up getting a 0 scene. Okay. So according to this, in case of a pull down circuit, whenever a switch is pressed, the signal rises from low level to high level, and as long as I have kept the switch pressed, I will keep reading a high level itself. So when I go with a pull down circuit, upon switch being pressed, okay, so you are going to identify a rising edge, and you are going to identify throughout the switch press a high level. Okay. Now I have a simple question. Assume you are asked to take the action at the low level of the signal. Okay. You are asked to take the action at the low level of the signal. Which circuit are you going to choose? Yes, it's always a pull-up circuit. You are asked to take the action at the rising edge of the signal. So which circuit will you choose? If it is a rising edge, you have to choose a pull down circuit. So depending on the circuit you are dealing with, and depending on the connection you have been dealing with, you can identify which edge and which level upon switch being pressed. Or if you are given a choice to select the circuit, depending on how you want to take the action, you can choose the circuit. So that is either a pull up circuit or a pull down circuit. Is that clear? Okay. So that is the basic of how tactile switch has been working, or how the switch can be connected to a pin of a microcontroller in two different possible configurations. Next, there is something called as bouncing effect. Now, before I speak about bouncing effect, have you ever seen how this tactile switch has been formed? Like, have you seen the hardware of how a tactile switch has been formed? Have you ever opened the circuit and checked how a tactile switch has been formed? No? Okay. No worries. I can show it up here. You can see this is how a tactile switch or a tactile key is formed. And if you can see, there are three different terminals here, and there is a half cut metal plate which has already been connected to two terminals. Okay, there's a half cut metal plate which has been connected to the two terminals. Now when you press the switch, so that pressure on the switch will be applied on the metal plate. This metal plate gets flattened, and it is going to establish the connection between the three terminals, and then it leads to the current flow, and you consider it as the switch being pressed. So this is how a tactile switch is actually framed. So there are terminals, there is a half cut metal plate, and you are going to put the pressure on this box. So whenever the pressure is applied on the switch, so this half cut metal plate gets flattened and it is going to establish the circuit between the three terminals. So that is something how a tactile key is going to work. Now the problem with this metal plate is the moment you press, it will not give you a constant signal. For example, have you observed the string of a guitar or the chord of a violin or any instrument that way? Like if you touch, have you seen the small vibrations which happens on the string? Have you seen the small vibrations? Or if you want to take a very simple example, stretch a rubber band. Okay, so stretch a synthetic rubber band and then you just pull and leave off the rubber band. So if you can see, if you can observe, there will be small vibrations being done by that particular band. Okay, so the same happens in case of this metal plate also. When you apply pressure on this metal plate, it will not make the connection at that moment itself. So there is like small pulses being formed. So connection may get formed, connection may not get formed. Again connection may get formed, connection may not get formed. So like that, due to the vibration, the connection is not definitely made the moment you press the switch. It will take few milliseconds in order to give the constant signal. Okay. So for example, if you take, assume this switch has been connected as a pull up circuit. Okay. So this is seen as a pull up circuit. So whenever you press the switch, what should I see? Whenever I press the switch, what should I read at the pin of the microcontroller? So if I don't press the switch, in case of a pull up circuit, yes, so I have to read a 0. So initially it will be 1. The moment I press the switch, I should be able to read a 0. And as long as I have kept the switch pressed, I should continue to read a 0, correct? So this is what I am expecting. But due to the bouncing effect, okay, due to the vibrations which are being made on the metal plate, before I get this kind of circuit, I might get some small pulses generated like this. Okay, some small pulses will get generated initially, and then I might end up getting a constant signal like this. Okay, now assume I am supposed to take the action at the falling edge. Okay. So one time I press the switch, ideally, how many falling edges should I identify? One time if I press the switch, ideally how many falling edges? I should identify only one falling edge. So I should end up taking the action for only one. But due to the bouncing effect, I might end up seeing multiple falling edges. So I'm seeing 4 in my case. Okay. So in the example I have taken, I'm seeing 4. It can be more also. Instead of me getting one falling edge for one time switch press, I'm getting multiple falling edges identified for one time switch press done. That is due to the bouncing effect. And this is going to affect my operation. So instead of me taking the action for once, I might end up taking the action for 4 times. So that is actually wrong. Okay. So remember, this bouncing effect should be taken care of in your software itself. So you cannot do anything into the hardware. So this is how hardware is being designed. So you cannot make any changes to the hardware. You always have to take care of this bouncing effect in the software itself. Now, how will you take care is, you will add a small delay. Before reading the switch, you will add a small delay. So this bouncing period, what you see, will be approximately from 20 milliseconds to a maximum of 50 milliseconds. Okay. So bouncing period can be varying from 20 to 50 milliseconds, and it depends on several factors. It depends on the metal plate you have used. It depends on the life of the tactile key. It depends on the quality of the tactile key. So it depends on multiple factors. The only way of taking care of this bouncing effect is with the help of your software. So before you taking the action, you should add a small delay of approximately 40 milliseconds so that bouncing effect is being ignored, and then you end up taking the action. So these times, whatever bouncing effect you saw, you don't have to take the action. So you just have to ignore it. And that is taken care of in the software only. The same thing happens if you, after you release the switch also. So even after releasing the switch, this bouncing effect might happen, and that also has to be taken care of in the software itself. So bouncing effect is the one which is happening due to the metal plate forming the connection on the terminal. So you have to avoid this bouncing period. So you can see this is the bouncing period, which is varying from 20 to 50 milliseconds when the switch is pressed and when the switch has been released. So you have to take care of it in the software only. Is that clear? Okay. So that is about the bouncing effect. Okay. The next we have got is to start with the programming part. But before that, you can see, in case of our PIC microcontroller, there are in case of our 16 lab board, there are 6 switches which we together call it as digital keypad. So let me identify those 6 switches. These 3 switches and these 3 switches. 6 switches from RB0 to RB5 are called as digital keypad. Okay. Can we go for RC rebounds externally? So however you want to take care of, you can do it. Okay, so not like this is the only way, but because we are doing a programming, okay, so because we are doing a programming into the embedded system, so it is easy to take care of it in case of the uh, software internally in your program. Okay, fine. So yes, I was telling that the 6 keys, whatever I have highlighted here, are the part of the digital keypad. So 6 keys together, we call it as digital keypad. Can you observe the circuit on board connection and tell me how is the circuit being formed? So how is the switch being connected as? Whether it's a pull-up circuit or a pull-down circuit. So look at only one switch and conclude. You don't have to see all the switches. Is it a pull-up circuit or a pull-down circuit? Pull-up? Okay. So for those who are not able to identify, you see, so one end of the switch is being connected to the ground like this. Okay. And another end of the switch has been connected to the microcontroller. So there is one resistor here. There is VDD here. Okay, VDD. And here there is another resistor, and then there is a pin of a microcontroller. So here is the switch. So every switch of the digital keypad is being connected as a pull-up circuit. So upon switch being pressed, you are going to identify a 0, and switch being open, you are going to identify a 1. And whenever switch is pressed, you are going to identify a falling edge, and throughout the switch press, you are going to identify a low level. Okay. So we are going to concentrate on only pull-up circuits, because on our board what we have is a pull-up circuit, but you should be able to program a pull-down circuit also, because right now you have the basics of how a pull-down circuit works. So in our case, because it is pull-up, we are going to concentrate on pull-up circuit only. So in tomorrow's class, first we will see how to configure one switch and take the action. Then we will see how to configure all 6 switches of the digital keypad and take the action accordingly. So I'll start with the programming part in tomorrow's class. So tomorrow we will start with the programming of digital keypad. We will configure one switch, both with level and edge detection. Then we will see how to configure all 6 switches. Okay. So hope today's class is all being clear. If you have got any doubts, please let me know. Okay. So here is your QR. Please have your attendance marked and then quit the session. Thank you for attending the class. We'll continue tomorrow. Thank you all.